Hello, and welcome to part 4 of this video playlist about the preparation of alkylarenes. In this video, we'll have a look at the alkylation of unsubstituted arenes with carbon-centered radicals and with carbon nucleophiles, for instance, ylides or polar organometallics. Because hydrogen atoms and hydride are poor leaving groups, these reactions often require oxidants to generate cationic intermediates. The reactions discussed in this video are organized as shown here. I'll start with specific examples of alkylations with radicals, then with ylides, and finally with carbon nucleophiles. When carbon-centered alkyl radicals add to arenes, one new sigma bond is formed, but a carbon-carbon pi bond is cleaved, and the aromaticity is lost. Radicals are less energy-rich than carbocations, and the addition of radicals to arenes can be slow, reversible, and energetically unfavorable. Re-aromatization requires abstraction of a hydrogen atom, what is often accomplished by oxidation to a carbocation, followed by deprotonation. Although the stationary concentration of radicals is low in most radical-generating strategies, radical dimerization can become an important side reaction if the addition of the radical to the arene is too slow. Best results are achieved with electron-deficient arenes and electron-rich radicals, or with electron-rich arenes and electron-deficient, that is, acceptor-substituted radicals. Unlike in the Friedel-Crafts alkylation, where the product becomes more reactive, an electron-rich radical will enhance the electron density of an electron-poor arene and thus slow down a second alkylation. Thus, alkylations with radicals will yield less over-alkylated products than Friedel-Crafts alkylations. A further advantage is that carbon-centered radicals do not rearrange as readily as carbocations. Let's check some specific examples. One convenient way to generate carbon-centered radicals is by oxidation of carboxylic acids. The intermediate oxygen-centered carboxyl radicals decarboxylate to alkyl radicals, which will only dimerize if their concentration is high, like on the surface of an electrode in the Kolbe reaction. In this example, pivalic acid was oxidized with diacetoxyiodobenzene, and the resulting tert-butyl radical alkylated the ortho positions of a palladium chelate of azobenzene. Overalkylation occurred because of the excess of pivalic acid and oxidant. In this instance, the product was metylated at the alkylated arene because electrophilic palladation occurs preferentially at electron-rich arenes. Here, isopropyl radicals were generated by oxidation of isobutyric acid with the electrophilic fluorinating reagent SelectFluor. Addition to 4-cyanopyridine occurred at position 2. Oxidation of protected glycine with ammonium persulfate gave an aminomethyl radical which added to a dihalopyridine with high regioselectivity. A number of additives were required to attain an acceptable yield. In this example, no free alkyl radical was formed. Acylation of a rhodium chelate with an acid anhydride and strong heating caused decarbonylation of an intermediate rhodium acyl complex and then alkylation of the benzamide. Heating diacyl peroxides causes oxygen-oxygen bond homolysis and decarboxylation. Here, 1,4-dichlorobenzene was alkylated with the pentyl radical generated by heating dihexanoyl peroxide. In this example, 3-methylbenzoic acid was heated with an excess of ditert-butyl peroxide and catalytic palladium acetate. A clean orthomethylation of the benzoic acid occurred. Under these conditions, benzoic acids form palladium chelates. And one possible mechanism would be methylation of such a chelate by methyl radicals, followed by reductive elimination of palladium. Alkyl radicals can also be generated by oxidation of secondary alcohols. Carbon-oxygen pi bonds are as strong as carbon-carbon sigma bonds, what enables the fragmentation of oxidized secondary alcohols into aldehydes and alkyl radicals. Here, an ethyl radical was formed by oxidizing 1-phenylpropanol with diacetoxyiodobenzene. Addition of this radical to a pyridine N-oxide followed by oxidation yielded the alkylated pyridine N-oxide. The oxidation of alkyl dihydropyridines can also yield alkyl radicals by homolytic fragmentation. In this example, isopropyl radicals were generated this way and used to alkylate a triazine dione. Here, a diacetyl peroxide was decomposed thermally, but the resulting electron-rich alkyl radicals did not add to the electron-rich aminopyrazine. Instead, these radicals alkylated a xanthate at sulfur, whereby the electron-deficient alpha-propionyl radicals were generated. These added to the heteroarene, and decarboxylation then yielded the observed product. Aminomethyl radicals have been generated by oxidation of methyl amides with persulfate. In this example, dimethylacetamide was oxidized this way, and the radicals were trapped with 4-cyanopyridine. Aminomethyl radicals, being electron-rich, add well to acceptor-substituted or protonated or quaternized pyridines. Also, the radicals formed by oxidation of ethers are electron-rich and can alkylate pyridines. Here, however, a ruthenium chelate was the reactive intermediate, and the THF-derived radical added para to the site of methylation. Electron-deficient radicals, like those obtainable by oxidation of ketones, also added to the methylated arene, again para to the carbon-ruthenium bond. Acetone nitrile can be oxidized to the cyanomethyl radical, which is electron-deficient and should add quickly to electron-rich arenes. Reaction with coumarin occurred alpha to the carbonyl group. Alkyl halides are also convenient radical precursors. Here, an alkyl iodide was oxidized with hydrogen peroxide, and the resulting radical then added to N-methylpyrrole. I'll show you now some examples of arene alkylations with ylides, mostly with diazoalkanes. These are nucleophilic at carbon and can react with electron-deficient arenes. Migration of a proton, elimination, and aromatization then yields alkylated arenes, as sketched here. The initially formed intermediate can also cyclize to a cyclopropane and rearrange either to a cycloheptatriene or to the alkyl arene. Alpha elimination from ylides may yield carbines. These can cyclopropionate arenes in a concerted fashion or yield alkyl arenes by CH insertion. If the concentration of carbene acceptor is too low, carbines will dimerize or rearrange to alkenes. In this example, catalytic rhodium converted a diazomalonate into a rhodium-carbene complex, which alkylated a phenyl ether at position 4. The solvent 4-chloro-trifluoromethylbenzene did not react with this electrophilic rhodium-carbene complex. Although indoles are usually attacked at position 3 by electrophiles, in this example, carbene CH insertion occurred with unexpected regioselectivity. The product's structure was determined by single crystal X-ray crystallography. Surprisingly, no alkylation of the naphthyl group occurred, which is also highly reactive toward electrophiles. The intermediate boron ylide formed in this example also had electrophilic properties and reacted faster with dimethylaniline than with the solvent xylene. Heating sulfonyl hydrozones with strong bases can yield diazoalkanes. Here, a copper-carbene complex was generated by heating a sulfonyl hydrazone with lithium tert butoxide and catalytic copper iodide. Insertion of this carbene complex into position 2 of a pyridinium ylide gave the alkylated heteroarene in 70% yield. Sulfonium ylides are more basic and nucleophilic than diazoalkanes, and are better suited for the alkylation of electron-deficient arenes. Few examples have been published, though, and some optimization may be required to attain high yields. In this example, nitrobenzene was alkylated with 3 different ylides. Mostly orthomethylation occurred, but the yields were low. Here, a sulfonium ylide was used to methylate quinoline N-oxide at position 2. Quinolines are more reactive than pyridines or simple nitroarenes, and the conditions given here will probably not succeed with monocyclic arenes. Let's check some alkylations with carbanions. If the carb anion is stabilized by a group that may also act as a leaving group, the alkylation of arenes can proceed by the same mechanism as the alkylation with ylides. Otherwise, the intermediate anionic addition product will have to be oxidized and deprotonated to regain aromaticity. For instance, methyl lithium can be added to nitrobenzenes at low temperature, whereby an anionic, non-aromatic intermediate is formed. Here, this intermediate was oxidized with bromine and then aromatized by dehydrobromination with triethylamine. Similarly, in this example, a silane was the precursor of a lactam enolate, which added ortho to the nitro group. Oxidation with DDQ then yielded the alkylated nitroarene. Ketone enolates can add to the unsubstituted para position of nitroarenes, even if these carry leaving groups at other positions, as in this example. Addition to an unsubstituted position is fast, and if the resulting intermediate is quickly aromatized by oxidation, the leaving group may not be displaced. Unfortunately, this reaction was conducted in DMSO, which can explode when heated with strong bases. Thus, for larger preparations, some other polar A-product solvent should be chosen, for instance, dimethylacetamide. Benzyl halides do sometimes react with soft nucleophiles, not at the benzylic position, but at the arene. Here, with an allosilane as nucleophile, a benzyl chloride was allylated para to the chloromethyl group. Deprotonated chloroacetic esters can also add to nitroarenes. The anionic addition product in this instance was unstable and eliminated hydrogen chloride. No additional oxidant was required for rearomatization. This type of alkylation is also called vicarious substitution. Such reactions can even succeed with lithiated dichloromethane as nucleophile. To avoid carbene formation by alpha elimination, lithiation and addition to nitrobenzene was conducted at -100 degrees Celsius, a temperature attainable with an ethanol liquid nitrogen cooling bath. Dichloromethylbenzenes can react in a similar way. Here, the base was added to a mixture of dichloromethylbenzene and nitrobenzene at -78 degrees Celsius, and the alkylation was complete after only 15 minutes. Also, benzamides are sufficiently electron deficient to react with polar organometallics. Here, a large excess of ethyl magnesium bromide was added to a benzamide in the presence of air and catalytic cobalt. The benzamide was alkylated twice at the ortho positions. This example is a variation of the Fischer-Indole synthesis. Strong heating of a deprotonated aryl hydrazide led to intramolecular addition of the enolate to the phenyl group. Cleavage of the weak nitrogen-nitrogen bond and cyclization then gave an indolone. Pyridines are electron deficient and react well with carbon nucleophiles. In this example, isopropyl magnesium bromide was added to a nitropyridine N-oxide, and the intermediate was then oxidized with DDQ. The sulfonyl group is both acidifying and a leaving group. Thus, deprotonated alkyl sulfones are suitable nucleophiles for vicarious substitutions at electron-deficient arenes. In this example, a nitropyridine reacted with a cyclopropyl methyl sulfone and a strong base. A high yield of alkylated nitropyridine resulted. The phenyl-thio group remained unchanged because addition to unsubstituted aromatic positions is faster than to substituted positions. Similarly, addition of an organolithium reagent to dichloropyrimidine occurred at an unsubstituted position. Oxidation with DDQ then yielded the alkylated dichloropyrimidine. Boranes are weak carbon nucleophiles only. In this example, a palladium chelate generated by oxidative palladation of an aryl acetic acid reacted with a butyl trifluoroborate. An excess of silver carbonate and various ligands and additives were required to attain a high yield. Here are some more examples that are also listed in the description of this video. Under the Posts tab of my channel, there is a copy of the slides. The next video of this playlist is about the alkylation of aryl halides and related electrophiles by substitution of the leaving group. See you there.